Okay, thank you very much. Thank you for being there on a Friday afternoon. And yes, what I want to talk is not new, and I said I'm not new either. So, but it was not. It was not published. So many things are published, but somehow there is something that was in the works and so on. So we decided to submit. Okay. So let me start with the history, with the motivation. So you probably know that all this comes from the work of Laborie in a paper published in 2006. Laborie was trying to understand what's a Hitchin representation. Hitchin defined it, studied a space of representations that was of the fundamental group of a surface into PCL and R. For n equals 2, this space is Tag-Muller space. For n equals 3, this space is a space of projective structures that have been studied by Goldman and Choi and Goldman, sorry. So he was looking for geometric interpretation of representations in this component, because Hitchin compute the component using some completely different techniques, okay? And then there is a paper, a very important paper by Olivier Guichard and Anna Winchard, where they generalize the notion to, instead of a surface group, a Gromov hyperbolic group, and instead of a PSLNR or SLNR, any semi-simple Lie group, okay? And it happens to be the analog of the notion of convex co-compact for hyperbolic groups, for hyperbolic space, just for higher rank. So with Misha and Bernhard, we decided to study this from the point of view of symmetric spaces. I will spend a lot of time talking about that. I have to mention also the paper by the work of Guerito, Guichard, Kassel, Winchard, and many people I'm forgetting. So many people we were trying to understand this kind of representations or groups, because I will confuse the group with the representation with its image, which is the group. And the purpose of today, if I succeed to manage the time, which is unlikely, is to talk about how to try to give a characterization of an Anosov representation, just taking finally many elements of the group. So this is why the title, there was the word local. So I give you finally many elements. Well, I don't know how many I will need, but just from finally many elements, I should be able to say whether my representation is Anosov or no. Maybe I should say something, okay? Okay, so let's go to the, before giving the definition, well, I have to point here, yeah? Before giving the definition of Anosov, I need to talk about parabolic groups. Parabolic groups or Flach varieties of Flach manifolds, yeah? So take a semi-simple Lie group. The definition of parabolic, P is a parabolic subgroup if the quotient is an affine variety, but we have, and this is what it's called the Flach variety. So the example we have in mind all the time will be SLNR. For SLNR, we have it's acting on the projective space of dimension n-1, and we know what's the Flach manifold here, or the Flach variety. Yeah, it's a set of flags, so it means a point inside a line or a one-dimensional submanifold, linear submanifold, and so on. So it's a sequence of submanifolds, that's a flag. All of them are linear and of codimension 1. And that's an example of Flach manifold. And here the parabolic group would be the group of upper triangular matrices, okay? So that the quotient is this Flach variety. In general, well, there are, let me give you another example, SL3R. Now there are 3 conjugacy classes of parabolic subgroups because you have the Flach variety, so the variety of Flachs in P2, but you have partial Flach varieties, so just P2 itself or the dual, okay? These are examples of Flach varieties. And there is a notion of being opposite, which in terms of flag varieties is duality, or well, it's an involution in the space of conjugacy classes of parabolic subgroups. Okay, so it corresponds to apply the Cartan involution in the symmetric space. In our case, would be to take the transpose, but it's the conjugacy class. So one way to think of opposition is writing in that way is just this involution. Okay. Here we have that P1 is opposite to P2. Yeah. So the projective plane is dual to its dual, the space of lines. Okay. And the flag manifold is dual to itself. And this is the parabolic subgroup. I write a B because this is often called the Borel. Well, this is called the Borel subgroup. That's the smallest parabolic subgroup. Okay. More examples of parabolic subgroups. So now, instead of SL3, I discuss SL4. Here there are 7 conjugacy classes of non-trivial parabolic subgroups. You have to imagine a stabilizer of points and lines, and so on, of partial flags. But then three of the classes are self-opposite. Okay, so this is symmetric, and this is symmetric. So the first one is the stabilizer of a point and a hyperplane. Okay, because this is self-dual. The second one is the stabilizer of a line. Okay, and the flag manifold is the variety of lines, and the last one is the stabilizer of a full flag. Okay? That's the full flag manifold, and these are partial flag manifolds. Well, I need this for the definition of Anosov. Another example, also rather easy. We can take a product of groups. My group has to be semi-sample, doesn't need to be simple. Okay, so it's just product of two. I take SL2R times SL2R. The symmetric space will be H2 times H2 because I'm taking the quotient. So here I have 3 conjugacy classes of non-trivial parabolic subgroups. In one fact, I take a parabolic subgroup in one factor and the whole group in the other factor, the symmetric, and just the product of parabolic subgroups. And all of them are self-opposite. Okay, they are dual from themselves, and we have three kinds of flag manifolds. The ideal boundary of H2 times a point times the ideal boundary of H2, and the product of the ideal boundary of H2. Okay, because I will not discuss this, but these flag manifolds, they live in the ideal boundary of the symmetric spaces. There are some orbits there. Yeah? And that's important. Okay, so this is just a fixed notation. Then what's the definition of Anosov group, of Anosov representation? So I start with gamma, a Gromov hyperbolic group, a discrete group, and rho, I choose as a conjugacy class of parabolic subgroups, which is self-opposite. Okay, the idea will be that the flag variety will be at infinity, but I will discuss this. So when a representation is called Anosov of P Anosov, because it depends on the choice of the conjugacy class of P. If I have 2 things, the first thing is it's an embedding, an equivariant embedding, beta, I think I wrote a beta, from the group to the flag variety. Okay, equivariant embedding. And it has to be generic. Generic, we call it antipodal, but just for the moment, think of genericity. It means the following thing. I have 2 different ideal points, sorry, and this goes from the ideal boundary. If I have 2 different ideal points, they go to generic flags. Okay, so flags are generic, the lines as generic as possible. Okay, that's what it means, an antipodality. And then this is just topological. Okay, so then I add something else. I have asked for a contraction property. What is contraction property? I take a geodesic, a word geodesic in geodesic right, sorry, normalized geodesic right, means that it starts at the neutral element and it's geodesic. And I look at the ideal point. Well, I want that when I go to infinity along this geodesic, the image, this is contracting. So this is the differential, the norm of the differential at this beta of the ideal point. Okay, so I have an ideal point. When I approach the ideal point here and I go to infinity there, well, sorry, when I approach the ideal point here, I look at the action on beta of infinity, and this is contracted. Well, this is a simplified version of the definition of Anosov, but it's a definition that works. And then why to call it Anosov? What they were calling Anosov, yeah? Well, because Laborie was working with the unit, with the geodesic flow on the unit tangent bundle. So this moving along a geodesic was giving with, you see it many times with a more technical condition, well, not more technical, something which is equivalent, but yeah, just taking a sequence of elements along a array, so you can state it in terms of the geodesic flow. And then Gisher and Binhar use the geodesic flow on gamma, but a geodesic flow in a worried hyperbolic group is something a little complicated to define, okay? So that's the definition of Anosov. And now I plan to talk a little bit about symmetric space. Yeah, something I forgot to say. Gisher and Binhar already proved that these representations are discrete and the kernel is finite. Well, in fact, Laborie for surface groups proved that the kernel is zero, that the representations are, how is it called, faithful. Well, in general, if you take a world hyperbolic group, if you multiply, you take the Cartesian product with a finite group, your group is still a hyperbolic, and things shouldn't change. So there is a trivial case. So instead of faithful, they have finite kernel. Okay, but that's the definition of. Yes. They act on the yeah. That's a good question. They act on this manifold, on the flag variety. So put any Riemannian metric there, and it's acting as a contraction around the point. Around you have a point here, and you have beta of this point. Okay, and it's acting as a contraction here. So this point is in the ideal boundary. So I have a sequence of elements approaching it. And then the corresponding representations, they are here and they are contracting. Okay. Pardon? Sorry, say it again. Well, okay, maybe I didn't understand what the first word. So, okay, sorry. So yeah, some examples, and maybe inspiring examples. The first one, it's a discrete subgroup of isometries of hyperbolic space. A discrete subgroup has a limit set, which lives in the ideal boundary, okay? And we have a convex hull. The convex hull is the smallest convex in hyperbolic space that accumulates to this limit set. So a group is called convex co-compact if the convex hull modulo was if gamma acts co-compactly in the convex hull. Okay, this quotient is compact. And now this happens to be the same thing as Anosov. What is the parabolic group here? Well, there is only one choice for parabolic group, subgroup, which is the stabilizer of an ideal point. Or if you prefer, the flag variety here is just the ideal boundary. Okay. So these flag manifolds, they live at infinity, and here the action is just this one. And if you know something about action of co-compact actions and so on, it's not hard to, this is a standard to see that it's equivalent because on one side, well, the group has to be, if it's convex co-compact, it has to be work hyperbolic, okay? The ideal boundary of the group, the Gromov boundary of the group is the same as the limit set. So we have this nice embedding. Here, everything is generic. You don't have to worry about that. And well, we have this contraction at the limit set. Okay, that's well, it's Sullivan. It's classical. Yeah. So the idea is that here we have this map, okay? And for seeing the equivalence, I'm using some, well, people have to use something here, which is, for the next one. So there is another way to, there are many ways to characterize convex co-compactness. And one of the nicest one, I think, is, well, one is this one, a group is convex co-compact, if only if the orbit map, so the embedding of the group into Hn via the orbit, that's a quasi-isometric embedding. It maps geodesics to quasi-geodesics. Yeah? And something here is easy to see, because if the action here is co-compact, so it will be quasi-isometric to the convex hull. But for the converse, one has to work a little bit. And essentially, one has a Morse lemma that says that quasi-geodesics are close to geodesics. Quasi-geodesics in Hn are close to geodesics. So when you have a quasi-isometric embedding, you have quasi-geodesics, then they are close to geodesics, and you end up being in the convex hull. That's it. Well, this is not the proof, but that's the idea of the proof. Okay. Another example, which was the motivating example by Laborie, was representations in the Hitching component. And here the parabolic subgroup is just the Borel subgroup, the group of upper triangular matrices. Okay. I will not discuss this example, but this is certainly an historical example, an important example. Yeah? And another example comes from projective manifolds. In fact, strictly convex and should have set proper closed projective manifolds. Okay, it's a manifold like this is D divided by gamma. D is a domain, a properly convex, strictly convex domain properly contained in an affine chart. And gamma is the subgroup of, is a subgroup, a linear subgroup that preserves this D, and the quotient is compact. And this is called Anosov, but here the parabolic group is the group whose flag variety is the partial flag manifold consisting of points and hyperplanes. Okay? And here the limit set of the group will be this. Well, the limits, I mean, the curve, the limit set of the group will be mapped to this flag manifold, and here we'll have the set of flags. So you have points at the boundary and hyperplanes which are tangent to this boundary. Okay, and that's an example of that's another example well known, well, because Benoit had proved everything before the notion of Anosov, yeah, and the group has to be hyperbolic and everything works, okay, and that's another example of P Anosov, and there are plenty of them. There are a lot of them. I will not discuss them, but there are examples of many examples of that. No, so I want, and now in the next slide, I guess I will discuss. Well, I guess, I should discuss the symmetric space, the point of view of symmetric spaces. So for instance, in this case, I will not work in the projective plane, but in a large symmetric space, okay? So symmetric spaces of non-compact type. I assume that you are familiar with symmetric space. Otherwise, a symmetric space is a Riemannian manifold complete with an involution at each point, which a spatial involution, which is called a symmetry. And there are two ways to present these symmetric spaces of non-compact type, two equivalent ways. One is say, okay, my symmetric space is the product. There is a RAM decomposition into irreducible symmetric spaces. None of them is compact. So each factor is non-compact and it's not flat, okay? I don't want flat spaces, just every factor is a symmetric is a non-compact irreducible symmetric space, or just say that the group, this G, which is the identity component of the asymmetric group, is semi-simple. Yeah? This means that I don't allow this, and K is a maximal compact subgroup. That's the stabilizer of a point, and I take it maximal compact. Okay, that's the standard way to think of symmetric spaces. Here we have, of non-compact type, sorry, here we have basic examples we will work with. Hn itself is a symmetric space, hyperbolic space. Basic example which we will work with is SLNR divided by SON. Okay, that's a maximal compact subgroup. Or the example I gave before, just a product of two spaces. And we are interested in this characterization of Anosov from the point of view of the action on the symmetric space. In this case, from the point of view of the action on X. I need to introduce some notations, some basic notations. So one is the notion of flat. A flat is a totally geodesic subvariety isometric to RK, which is flat. And this gives me a big difference between the hyperbolic space and the other two examples, is that there is the notion of rank. The rank is the dimension of a maximal flat. And why this notion is important? Because a maximal flat gives me zero curvature, okay? So first thing, the rank is well defined because all maximal flats are congruent. So G acts transitively in the set of maximal flats. They're all the same. They are all congruent. And the curvature, the sectional curvature of X is non-positive and is strictly negative. It's negative if and only if the rank is 1. So for instance, for hyperbolic space, if the rank is at least 2, we say that the space has a higher rank, because that's when it has zero curvature. Okay? And more or less the idea or the philosophy or this blah, blah, blah about what Anosov means, these Anosov subgroups, they try to have a negative curvature behavior, but having higher rank. So the idea is to try to reproduce what we can do for hyperbolic space. We'll try to do it for symmetric spaces. And we have to deal with flats. Flats will be our program, okay? So let's talk a little bit more about flats, or just let me just give you a couple of examples. For instance, for my favorite example, SLNR divided by SON. Here the rank is n-1 because here is an example of flat, maximal flat. Not only flat, but maximal one, okay? So take diagonal matrices and the exponential, I write it in that way as the exponential of a Cartan subalgebra. And I ask that, well, the determinant has to be 1, so I ask that this addition is 1, the trace is 0. So that's you can check that this is a flat of dimension n-1, no? And this gives me that the rank is n-1. This is well known, of course. For Hn, the rank is 1. If you take a product, so the rank is additive by products because you take products of flats. Huh? That's not difficult. And I need to introduce a tool which is the Weil subgroup, or the Weil group, sorry. I can think of the Weil group as the stabilizer of the pair consisting of a maximal flat and a point. Okay? So these are elements of these are isometries, elements of G that preserve the maximal flat and preserve a point. And what is very nice from all this theory is that this group acts as a Coxeter group on the flat. So it's generated by reflections along walls, and a fundamental domain, it's a Coxeter group, and the walls of a fundamental domain delta, which is called the Weil chamber. Okay? Example. A quick example is, again, SLNR over SON. W, the Weil group, is a group of permutations of the lambda, because you have permutation matrices here, yeah? Just take a just take a permutation matrix, and then this is acting on your flat, yeah, because it's we are working in the quotient, so it's equivalent as acting by conjugation. So a fundamental domain will be given by these equations. Yeah. For instance, for n equals 3, this is a plane. The equation is just one, yeah. And we divide the plane into 6 regions. The Weil group is generated by reflections along these 3 lines that permute the lambdas. So I represent it in that way. Here corresponds to lambda 2 equals lambda 3, and here corresponds to lambda 1 equals lambda 2, and here the other 3 values are the same. So this is a way to represent the group, the maximal flat and the action of the Weil group, okay? So this example, this is an example in rank 2, yeah, because the maximal flat has dimension 2. In rank 1, the Weil group is just the inversion of a geodesic, okay? And these are very important for the geometry because one of the things that is telling me is that symmetric spaces, they are homogeneous, of course, but they are not isotropic. And the directions will have different behavior. So I need to discuss a little bit more these Weil chambers and this stuff because this is important on how the geometry goes, okay? And its example is H2 times H2, so a flat is a product of geodesics, okay? L1 times L2. Each one is aligned on each hyperbolic factor. And here the Weil group, it acts as pi rotations on each factor. So if I have a point and a maximal flat, 2 lines along this point, so the Weil group is acting by a reflection here and a reflection there, okay? So it's Z2 times Z2, and the Weil chamber here is just the product of two rays going to infinity. So it's a quadrant, yeah? And maybe one thing that is worth to remark that I will put as a lemma, but we'll see first in one example, is that, okay, how many flats, so we ask how many flats contain a given line. So it depends, it will depend. So if I take this horizontal line L1, this is contained in many flats, yeah, many maximal flats, okay? Because if it's in L1, it means that this coordinate L2 is fixed. So this line will be, the horizontal line will be L1 times P2. Okay? I fix this. Well, this P2 is contained in many lines, yeah? So it's contained in many maximal flats. And same thing for the other factor. But if I take another one, a line with some slope, okay, so somewhere here, this will contain it in only one maximal flat. Is this important? Yes, because if it's contained in a lot of maximal flats, the curvature, there is no way that will be negative in any direction. I mean, so flats give me 0 curvature, so if lines are contained in many flats, they are not going to have the negative curvature. Well, things are not going to work well. Okay, so I take the following definition, take a line in your symmetric space. If it's contained in a unique maximal flat, call it regular. If it's contained in more than one, and in more than one, it happens to be infinitely many, but just say more than one, call it singular, okay? And singular lines or singular geodesics are those which are not in walls, contained in walls. That's the lemma. And here I had another quick example. So SL3R mod SO3, so the maximal flat was this one. An example of maximal flat is this plane. And I have the Weil group and the three walls, sorry, okay? The Weil chamber is 1/6 of the plane. And for instance, if you take one of the walls, lambda 1 equals lambda 2, so the first two eigenvalues are the same, you can conjugate by this rotation, okay? You can conjugate by this rotation, so your maximal flat will be contained in all conjugates of this flat. So your flat is contained in mainly maximal flats. And in fact, that's one of the characteristics of the geometry of symmetric spaces. Yeah? If you go along a non-singular line, it's contained along a regular line, there is only one maximal flat. There is always one, by definition of maximal. But if you go along one line, it's only one maximal flat. A regular direction, sorry. If you go along a singular direction, there are many maximal flats. Okay, so I need to worry about regularity. I need to give a definition. So if I give you 2 points, x and y, in the symmetric space, there is always a maximal flat that contains them, okay, that contains the segment. And I will take a Bell chamber with tip in first point x and containing the second point y. So there is a maximal flat, and I consider the Bell group fixing x and the flat, and I can define a Bell chamber. The Bell chamber there can be more than one a priori, but if it's regular, there is only one chamber. Yeah. If this segment is regular, there is only one maximal flat and a Bell sector having this property. Okay, not in a wall. Well, in rank 1, this will be just the ray that goes from x, leads from x to y and to infinity. Okay, and I strengthen the notion of regularity. I need to quantify this. How far I am, how regular is this? So I take the quotient of the distance to the boundary of the chamber, of the Bell chamber, by the distance to the tip of the chamber, okay? So I call the segment epsilon regular if it's larger than this. I give you an example with matrices. You can compute this with matrices. It means the following thing. I start with the identity and then take for the moment a diagonal matrix. Okay, so you have to keep in mind the picture we had before of this is lambda 1 equals lambda 2 and lambda 2 equals lambda 3. Maybe this is not the best color for the blackboard. And how do I measure the distance to the boundary? So I take this minimum of the difference of eigenvalues and, well, divided by this. Well, maybe there are some constants. This is not absolutely true. There are some constants missing here, but I don't want to compute them. But it's essentially true, okay? Regularity means that the ratio between eigenvalues in the diagonal case is proportional or stays between this distance between logarithm of eigenvalues and this thing and the distance to the origin, the norm of the matrix is bounded, okay? So the eigenvalues are not approaching, they are far enough, okay? If your matrix is not diagonal, we should look at eigenvalues of the singular values. And in fact, I should take it the logarithm, okay? So the eigenvalues of the transpose times itself, yeah? Because we are in the quotient bias of 3, and that's the way to compute in which Bell chamber we are and so on. Yeah? So the idea beyond this is that, okay, if we move along a regular direction, and now I add a direction which is perpendicular to the Bell chamber, if this direction is regular, they span a tangent plane with negative curvature. And in fact, you can compute that. You go to Helgason, and you look there, and that's the idea. And this curvature is bounded in terms of this epsilon. Yeah. Perpendicular means that it's a plane. It's taken another direction with angle pi over 2. Sorry. Any direction. No, to the chamber. So this lives in a higher dimensional space. Okay? For SL3, this is a 5-dimensional space. Take any. In fact, perpendicular to the flat should be. I should say to the flat, thank you. Perpendicular to the flat. If you move perpendicular to the flat, well, it depends if, and you add a direction in the flat, well, if the direction is singular, well, if it's regular, you know that the curvature will be negative, okay? And that's what motivates this definition, the definition of uniform regularity, okay? So we say that the discrete subgroup of G is uniformly regular if for any 2 elements of the group whose distance well, you fix a point, and if the distance of the orbit is larger than some constant, if they are far enough, then the segment is uniformly regular, meaning that the slope with respect to the walls is not zero. It's away from zero, epsilon away from zero, okay? And, well, it's for some constants, given this such and such and such. If there are some constants that this satisfy, we call it uniformly regular. You change the point, you will have to change the constant, but you can check that. And then there is another notion which is undistorted, which we saw before in the rank 1 case, that a subgroup is undistorted if it's finally generated and this orbit map is a quasi-symmetric embedding. So it maps geodesics to quasi-geodesics. Yes, and the theorem says that we proved some years ago is that a group is Anosov. I just take to the maximal minima parabolic subgroup if and only if it's uniformly regular and undistorted. Okay. So in the rank 1 case, we don't have this condition uniformly regular. So what we do in higher rank is we try to reproduce the things in rank 1. We need to add regularity, and we need to add things. And in this case, what we need to add is uniform regularity. Okay. So the remarks are the following one. Firstly, that uniformly regular are undistorted implies work hyperbolic, yeah, which a priori was non-trivial, but you have the group itself is work hyperbolic because that is in the definition of Anosov. The second one, I work with this parabolic subgroup because, well, I'm already giving a lot of definitions. You can work, if you work with different parabolic subgroups, you need a different notion of regularity. So this regularity has to be with the parabolic subgroup, but it's not, if you change the parabolic subgroup, you have to change the definition of regularity. And, well, it becomes a little bit technical, I agree, but for me, it's natural. And as I said, in rank 1, you don't worry about this, okay? So the idea is things that work in rank 1, try to translate them in higher rank, for instance, adding uniform regularity on these kind of conditions, okay? Okay, so what we want to do in the last 12 minutes, what I want to do in the last 12 minutes is find sufficient conditions now from finally many elements of the group, okay? And how can I do that? Well, to do that, I need to quantify things. I need to work with constants, with explicit constants. And I need to introduce another notion, unfortunately. Okay, I always think that I can talk for 2 hours, and then I have, but okay. So, and this thing will be the Morse property. So let me start with a definition. It's the following one. I will define a diamond, which is the following thing. So imagine that I have 2 points in a symmetric space that are joined by a regular segment, okay? If they are joined by a regular segment, then there is a sector, a Weyl chamber with tip X that contains Y. And this is unique. It's unique because of regularity. There is only one maximal flat, and in this maximal flat, there is only one Weyl chamber. So I take the intersection of this Weyl chamber and it's symmetric. So the other one is the chamber with tip on Y that contains X. So this has tip on X, the other one has tip on Y, and I take the intersection. And this is called diamond. I make a picture in dimension 2, but already for SL3, you have to imagine, or you don't have to imagine it, but you have to understand that the picture is in dimension 5, okay? So that's the intersection with a flat. Maximal flat is that nice. The intersection, the real object is even nicer, but in dimension 5 or in dimension whatever, okay? Well, now come the constants. So I prefer for that. The idea is that we'll try to use Morse lemma, but instead of working with geodesic segments, we work with diamonds. Okay? You know, Morse lemma is something intrinsic in hyperbolic space. It doesn't work in R2. you have a quasi-geodesic in R2. There is no way that it can be close to a geodesic. Yeah, this is, and the example is very easy. This is a quasi-geodesic in R2, and you take it very large and very far from a geodesic. So how do we deal with this in symmetric spaces? Work with this kind of objects. Okay. So instead of Moore's lemma will tell me that under some conditions, quasi-geodesics are not going to be close to geodesics, but to this kind of object, to diamonds, okay? So now come the constants. Essentially, we give a definition of Moore's group, and a Moore's group is a group that satisfies Moore's lemma. A Moore's lemma means, well, is that it's undistorted. It means it's quasi-regular. There are a lot of constants, but the idea is rather simple. If I have a geodesic segment of some length, but at least something, yeah, I'm interested in coarse geometry, at least some scale. The segment of an orbit is regular. This was uniform regularity in the previous slide. The orbit is a quasi-geodesic, okay, and this should be sufficient to be a convex Anosov. Well, no. If I work with constants, I have to add something else. Is that the image of an orbit? So I take a segment on the group and I look at the orbit in the symmetric space. It's close to the diamond. Okay. This d of the orbit of a point for e between 0 and n. So this orbit here, it's close to this diamond. Yeah. And well, I put this in form of a theorem, but this is what we are really using. Yeah? That instead of Moore's lemma, we have this kind of thing. Yeah? So that's stronger than uniform regularity, this Moore's assumption plus undistortedness, but it happens to be equivalent. Huh? And here we had to work a lot, Moore's lemma and so on. So I will not discuss this. But we are in the good direction. We are in the good direction because we are working with constants. These are bad news because always when you see a slide with a lot of constants, well, it's not very exciting. But if we want to do local things, we have to work with constants. So here I have geodesics of length at least some n, some scale, okay? And then there are the constants of being regular or being quasi-geodesic, and the d of being close to instead of being close to what? To diamonds, okay? So if I want to give a local notion, I cannot consider arbitrary length geodesics, so I have to restrict to geodesics of some scale, okay? So the next slide, I define what we call local Moores, and here it is. And instead of n, I have a scale. S will be the length of the geodesic segments. So I call, well, I work with representations now from the discrete group to G, and the group is work hyperbolic. So I have a representation from gamma to G. I said that it's local Moores with this constant, blah, 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 at some scale. This scale is the length of the segments, okay? And it satisfies every segment in the group, from the identity to some point of length S, satisfy these three properties. The first one is that it's quasi-geodesic, and that's the role of LNA. The second one is the regularity, this is slope with respect to the walls, that's the epsilon. And the third one is that it's close to the diamond, okay? And I call this local Moores, but I have to give the constants of locality. And the result is that, well, the first thing to remark is that if it's being Anosov means that being Moores, and it's more for some constants and some scale, S, and larger than that, for this scale and the scales that are even larger, okay? And the important, interesting theorem is going from local to global. So you have local Moores. So now I fix the constants here, which are well, I fix the symmetric space because the constants depend on the symmetric space. The constants epsilon, L, R, D, and so on that these properties hold. I find, or there exists an scale S. In fact, we can find an scale S such that if I have a representation with local Morse at this scale, then it's Morse and it's Anosov, okay? So the theorem says that for sufficiently long path, but for some length that depends on the other constants, if these constants are satisfied, then it's global Morse, and it's Morse with some other constants. I mean, there's no point about giving you all the constants, but it's Anosov, okay? So all these technical things that tell me that there is a way to check that, okay, with these elements. And, well, I have 4 minutes left. I will choose to talk about the application. Let me just give an application. There are several applications, but there is one which is interesting, which is semi-decidability. What does it mean, semi-decidability? It means the following thing. If I give you a work hyperbolic group and a representation, then there is an algorithm that stops if and only if it's Anosov. Okay? This is not decidability. This is semi-decidability, because if it's not Anosov, I will never know, because we will know to stop. Yeah? And I have constructed everything so that it works. So the algorithm is the following one. You fix some n. I will fix some integral, and we apply for n, we give some constants, a small one epsilon r over n. This was the slope with respect to the walls, the regularity, and some other constants, which are, these are the quasi-isometric constants, L and A, and this is the distance to the walls, 3 large constants. Apply the theorem, there is an scale S, so that if it's local Anosov for these constants, then it's Anosov. So I check for this scale S that depends on n. This should be Sn. If this is local Anosov. If it's Anosov, local Anosov, I'm happy. It stops and it's okay. If it's not, I proceed to n plus 1. Okay. If it stops at some point, it's Anosov by the theorem. But if it's Anosov, it has to stop. Why it has to stop, I didn't put on the slides, because the idea is that when n goes to infinity, these constants are more relaxed. Okay? If I have an LAD, I have an n quasi-isometry with L and A equals n, it will be also quasi-isometry for larger constants, but trivially, yeah? And if it's epsilon regular for 1 over n, it will be regular for 1 over n plus 1. So I have to choose the scale that it's growing, but that's okay, because I set every scale sufficiently large. So at some point it will stop. Well, there is an issue. There is an issue that if I want to have an algorithm, I need that this S has to be computable, yeah? Because but the proof we do, it's not computable. So it's not our corollary, it's the corollary of us and Max Ristenberg, who gave an explicit proof, constructive proof, I should say, of this kind of result. Okay, this can be computed. Probably the algorithm is not optimal, but I don't care. It's theoretically okay. Can we decide if there is an algorithm to decide whether it's Anosov or not? I don't think so, because there is a well, the first remark is it's only semi-decisible because it may not stop. The second one, it was not before, I think, even in rank 1, even if the proof in rank 1 is not too hard, is to use Moore's lemma by pieces and to glue geodesics. And there is a result of Misha Kapovich that say that discreteness for 2 generator groups in the isometry of H3 is undecidable. Is undecidable for something that it's called the Bloom-Sharp-Smale computability theorem. I don't know if you are familiar with that. I'm not. It's just It's a computability theorem more powerful than a Turing machine. If it's not decidable for that, it's not decidable for a Turing machine. This is using real numbers and algebraic varieties and so on. So you cannot decide discreteness. And I guess that you cannot decide that, okay? And well, I will not say anything about the proof. The idea of the proof is, well, I have the picture here. You have a quasi-geodesic by pieces in hyperbolic space. You can do some techniques in hyperbolic geometry and to glue them. And if it's sufficiently long, it will be if long segments are quasi-geodesics. Using Moore's lemma, you can prove that you have an indeed geodesic, okay? Because you can estimate the angles and so on. In higher rank, you do the same thing, suffering a lot because you have to deal with zero curvature, but it's essentially the same proof. And I will stop here. Thank you.